First we covered the double slit. I can extend that into the diffraction grating, where in this case, I'm going to look at the separation between each individual part of the grating to be given by D, just like I've done this before. Now, since I've got the case like before where the distance to the screen is much larger than the separation between these slits, then I hope that you can see why the diffraction grating makes sense to come right after the double slit, because if I am looking at some point then I'm going to be drawing a line from each of these places in the diffraction grating, etc., to that point. But at a maximum of two slits, if I take two adjacent slits and find them next to each other and say, oh, okay, here's the brightest point for those two slits, that's going to be a maximum for all of those slits because they're the same separation apart. If these two rays are one wavelength apart, then the separation between these two will be 2 wavelengths, 3 wavelengths, 4, and so on. It's still going to be a maximum. So when we construct through this, we'll find equations that look very similar, although in this case, we cannot assume that the angle is small, less than about 10 degrees or a sixth of a radian. We cannot make that assumption. So I need to leave, because these work at much larger angles. So I need to leave this in terms of, for maxima, the sine of that maxima, if this is some angle theta, well, that's equal to m lambda over d, because that last little step, this last little difference of lambda between two adjacent paths is basically the hypotenuse of the of this triangle, and this opposite side will be that side d. So the sine of that would be m lambda, however many steps of those are, divided by d. And we need to keep it in that form. So if I want to find the locations where those maxima occur, then I need to write that still in terms of that angle. I can find this angle by saying, oh, okay, that angle is the arc sine of m lambda over d. And then I can find the location of those places by putting it into there. And because the intensity is equal to the amplitude squared, I can take what I did for 22.2, reconstruct that, and the intensity of this light for the diffraction grating will be equal to n squared, where n is the number of slits times I. So that's one reason why we use a diffraction grating. Well, two big reasons. First, diffraction gratings work over much larger angles, and so they're much easier to read. And second, the brightness at the bright points is much higher than for just a double slit. This means by saying n squared here, that means that more and more of the energy, I mean the same amount of energy is coming through these slits as coming through, say, two larger slit sizes. But it's being more heavily concentrated at the bright spots, so the bright spots stand out much better.